All right, let's begin by talking about quantum mechanics and density functional theory and how does it fit in for engineering applications, especially mechanical engineering. So for the schedule of this module, we're going to talk about quantum mechanics, density functional theory, theoretical foundation on density functional theory, how to apply DFT in practice, and the application of DFT in mechanical engineering. In this particular module, we're going to learn about the fundamental principles of quantum mechanics, introduction to density functional theory, and their significance. So before we go in DFT, let's take a look on the physical domain that as an engineer and scientist that we typically deal with. So based on the scientific phenomena that you are trying to study, and based on the particle mass and particle velocity, you might be using different types of physics. So in this picture, we see 4 blocks, one for Schrodinger equation, one for Newton equation, one for Dirac, and one for Einstein equation. And on your x-axis, we see the mass, and the y-axis is the velocity. And C here represent the velocity of light, which is 3 into 10 to the power 8 meter per second, and mass of electron or mass of proton, which is represented by AMU, which is 1.66 multiplied by 10 to the minus 27 kilogram. Now, in the plot, if you look at the left corner, where we are dealing with free electrons, which have mass lower than the mass of protons, usually 10 to the power minus 31 kilograms, and velocity usually much lower than the velocity of light, then we should be using Schrodinger equation. Such as if you want to study electronic structure of a material. However, when we try to study larger systems, and which is usually the case for the mechanical engineering applications, we usually deal with Newton's equations such as atoms, coarse-grained models, and so on. So usually we'll be dealing in your mechanical engineering course the Schrodinger equation and Newton equation. However, there could be other domains of application, such as if your velocity of the particle is very high and still quantum in nature, such as the cold electrons, we're going to use Dirac equation for that. And if you're dealing with very heavy objects with very high velocity, such as the Large Hadron Collider, then we'll be dealing with Einstein equation. So as you can see, based on the velocity and the mass, we can categorize them into relativistic and non-relativistic equations. So usually we'll be dealing with non-relativistic equations, which is Schrodinger equation and Newton's equation for our mechanical engineering application. Unless you are designing a Hadron Collider and so on, then you'll have to think about relativistic equations such as Dirac and Einstein equation. So let's move on with Schrodinger equation first. So when we talk about quantum mechanics, as we showed in the previous slide, in classical mechanics, we deal with a deterministic collection of interacting particles. It may be atoms, it may be objects whose positions and velocity evolved according to Newton's equation of motion. That's classical mechanics. However, in quantum mechanics, the systems are described by a mathematical object known as wave functions, which depend on the position of all electrons and nuclei in the system. And this wave function of the electron evolved over time according to Schrodinger equation, for which he was awarded a Nobel Prize in 1993. So you might have heard about Schrodinger cat equation. So here the phenomena is the Schrodinger cat is alive and dead at the same time. So that's kind of the probability theory and what is it based on. So Schrodinger equation can also be represented by this H psi over E psi, very famous equations. The psi is known as the wave function. That's a way to represent a particular object. So for example, in this left-hand side, the dead cat and the alive cat and their combination represent one wave function. Now this Hamiltonian is represented by a matrix function usually, which we learned in our mathematical foundation module. And if you take the matrix eigenvalue, that will give you the energy of that system. Now this matrix representation can also be represented by a mathematical equation in terms of differential equation. So in this part on the left-hand side, we see kinetic energy, which is the second derivative of the wave function, and the potential energy, which is the wave function is a function of the position of the particle and its potential profile, and that gives the total energy. So you see all the things that we learned from the previous modules about linear algebra and differential equation can be very handful for such kind of applications. Some of the key aspects of quantum mechanics. One of the most fundamental principle or fundamental example of quantum mechanics is wave-particle duality. We describe how every particle or quantum entity can exhibit both particle and wave-like behavior, such as the electrons or light in the double-slit experiment. So here light behaves as a wave when it creates an interface pattern, and as particles, photons, when detected individually. So de Broglie wavelength is a characteristic wavelength for a light and given by the lambda wavelength, and h is the Planck's constant, and p is a particle's momentum. So let's look at this phenomenon in a animated video. So in this experiment, we demonstrate a quantum object. Here's a particle sent to two slits. They are touching the screen randomly. So this is the particle behavior. Now wave behavior. Now a wave is sent on two slits which make an interference. And this results in fringes on the screen. So usually a particle won't make a fringe screen. Now a quantum object is sent on the two slits. A quantum object is sent on two slits. The wave suddenly collapses into particle when touching the screen. You see it has some sort of both particle and wave-like feature. Now, if someone measures through which slit the wave goes, then the wave suddenly reduces or collapses and goes only through one of the two slits now. So this is not a perfect example, but definitely a good animation for showing the wave particle duality of the quantum mechanical principles. Moving on. There are some other principles that are in play. So uncertainty principle. So as we saw in the previous slide, electrons such as which follows the Schrödinger equation can have small mass and velocity with velocity comparable to the speed of light, such as electrons. So they follow the Heisenberg uncertainty principle, which basically means that it is impossible to simultaneously allocate the exact position of momentum. However, there is an equation which relates their momentum and their position, which is represented by P and X by inequality. So that is uncertainty principle. Now, as we saw in the previous slide as well, the alive and the dead cat. So in addition to that, we can have quantum states similar way, where the quantum states are the specific state in which quantum states systems can be. And they are described by a wave function which encode particles' quantum properties. Now, very interesting principle of quantum mechanics is superposition principle, which states that quantum systems can be in multiple states at the same time until it is observed. So this cannot be part of the classical mechanics. For example, Schrödinger cat through experiment illustrates superposition, showing how a cat in a scaled box is simultaneously alive and dead until it is observed. And finally, Born-Oppenheimer equation or approximation, which is to decouple the wave function of electrons and the nuclei. So when we solve actually DFT equation, we try to kind of we try to exclude nuclei from the picture so that it's easy to solve the equation. Now let's talk about the density functional theory. So density functional theory is a method in quantum mechanics, and there are many other methods. So this is not the only method, such as the many body perturbation theory, coupled cluster theory, and so on, Hardy-Fock theory, and so on. The density functional theory is very popular because in this one, you can consider if you have a simple beam and you want to simulate that, the number of electrons in that beam is millions or maybe more, right? So if you want to simulate that system, millions of electrons using Schrödinger equation, is intractable. So however, we can take a small portion of that beam and suppose it's made of aluminum. Now that aluminum, we can simulate a perfect aluminum with DFT or density functional theory. So there, instead of again solving Schrödinger equation, which is very challenging, we will be using something called Kohn-Sham or density functional theory equation. And because they use density, the charge density or electron density instead of wave function, that's why it's called density functional theory. They were awarded Nobel Prize in 1998, both this gentleman, Walter Kohn and John Pople. And these are the two famous papers in homogeneous electron gas and self-consistent equation, including exchange and correlation effect. So for which they were really famous for making this possible to apply quantum mechanical principle for mechanical or materials applications. So this is great, but how does it apply for mechanical engineering? So for DFT to be applicable for engineering application, it has several implications. So first, it is versatile. So this DFT is applicable to a wide range of materials. It can be different metals, semiconductor, insulators, nanostructures, composites, and so on. Accurate property prediction. Suppose you are trying to predict a new material, then you can predict its electronic properties such as the electronic band gap, transport properties, mechanical properties such as elastic constant, hardness, response to stress, thermal properties such as thermal conductivity, thermal expansion coefficient, and so on. It's also very useful for cost-effective research tools. Suppose you want to reduce the need of expensive and time-consuming experimental procedures, or you want to allow the examination of materials before synthesis, then this can be a very useful tool. It can also be used for design and optimization, such as facilitating the discovery of new materials of particular application, or it can support the more efficient energy applications such as photovoltaic or batteries. So it can also influence on innovation, such as if you are working with same types of material over and over, you might not be able to reach the optimal performance until you have discovered a new material or you have understood what limits the applicability of that particular material or method. For that, you might need a particular innovation where this kind of methods could be useful. And it also enhances collaboration across physics, chemistry, engineering. And so it's a fascinating tool to be familiar with.